Hello everyone, welcome to the third lecture on deep learning. Now this lecture is going to be a little bit different to the standard lectures because we're not going to be just following through slides and walking through examples. Instead, this is going to be a live coding session where the aim is really to help you get familiar with PyTorch and comfortable with writing the code required to construct and design modern deep learning architectures. So why are we learning PyTorch? Why are we not learning TensorFlow, Keras, Theano, or so on? Well, if we go back a few years, just looking at our research group, we all used to start using Theano, and then when TensorFlow came out, we all jumped onto this big ship, which was driven by Google with this large marketing drive behind it. TensorFlow was great because at the time, lots of papers were being written in it, and it's very powerful, and it had shorter compiling times compared to, say, Theano. So what do I mean by compiling? Why are we talking about compiling if we're writing Python code? Well, TensorFlow was built on top of what's called a static graph. So as you saw in the last lecture, we needed a computational graph to do automatic differentiation, the reverse mode of differentiation. So the way TensorFlow worked was you would write your Python code in these kind of abstract graph nodes and edges, and it would get compiled into this graph structure, which would then be used to optimize the automatic differentiation. But when PyTorch came along shortly after, PyTorch was built using a new paradigm called a dynamic graph, which is where you actually write your Python code, and as you're writing it, implicitly under the hood, a graph is being created on the fly. And it turns out this is much more useful, and you can, a lot of the state-of-the-art architectures actually require a dynamic graph to have more dynamic architectures which change over time and so on. So, and when you make an error in your code, the error that you get is actually where the code is, not just in some abstract graph structure. So TensorFlow and the other libraries realized this was like the thing, so they started to hack in this dynamic graph functionality into their libraries, but it never really got to the same level of maturity that PyTorch has got to, and now it seems Google is starting to shift their efforts into new libraries like JAX, and Julia is also starting to be a new emergent with their Flux, a new emergent library. So PyTorch is currently what most researchers are using to implement their state-of-the-art papers. So when you go on to some new journal or conference, you'll often see a lot of the implementations are in PyTorch. There's still a few in TensorFlow, of course, but the majority of them are in PyTorch, and soon there'll be a PyTorch implementation anyway if there's a good enough paper. So at the moment, I think it's the best thing to be using, to be learning, but remember, if you've learned PyTorch, it's very easy to transfer to another library later on down the line because the concepts are more or less the same. Okay, so with that start, I'm going to be teaching this lecture on my home machine where I've got a GPU, but I'll also be saying how you can connect into a server, and a lot of the principles that we'll learn today you can just use straight in Colab like in the coursework. So let's get PyTorch first. So I'm just going to first of all set up a Conda environment. So I'm just going to Google, I'm typing in mini Conda, and I click this link here. Then I'm using Linux, so I'm going to get the latest version of Linux, which is this link here. I'm going to right click and copy that link. Now I'm going to go into a terminal, and I'm going to make a new directory, call it ML test. So I'm just moving into that directory. So I'm in this new empty folder. I'm just going to download that file. Okay, it's just downloading now. This is going to be what I'm going to use to set up my Python environment where I'm going to install PyTorch and a few other libraries. Okay, that's downloaded. Let's just have a look at it. There it is. I'm just going to make it executable. What have I done wrong? Sorry, ch1 a plus x. Okay, so now if I look at it, I can execute that. I'm just going to run this script. So it says, would you like to install it? Press enter to compute it. Yes. I've already read that, so I'm going to say yes. I'm going to just stick it in this directory here within this folder. So it's now just downloading all of the files required for a complete Python environment. No, I'm not going to initialize that. And basically it's created this folder here, mini conda free, which I can set as my default Python environment. So I'm just going to go source miniconda free /bin/activate, and now you'll see I've got this sort of new thing in my command line, which means that if I install things with pip, like PyTorch, it's going to get all installed into this folder. So if I remove this folder, I'm back to having a clean installation again. and that's much better than using your system Python environment. You should never just, without creating this sourcing into your Conda environment, just pip install things, because that's going to break all of your default operating system Python dependencies. So you should always install into like a virtual environment. I'm going to pip install Torch and Torch Vision. We're going to be doing a little bit of work with images today. Also, I'm going to use a library called Visdim, which is going to allow us to visualize data, and also Ipython, because I want to code in an interactive Python session. So I'm just installing all of these. And this takes a bit of time, so I'm going to instead just Control-C and use a version I've done earlier. So I'm just going to cd out of that. And I've just done this already and downloaded everything. I've also downloaded a couple of datasets which we're going to use in this lecture. Okay, so now I've basically installed Torch and Ipython and Visdim, so I can actually just start an Ipython session and import Torch. But the first thing I want to do is use this data visualization library called Visdim. So I'm going to use something called tmux, and it's worth mentioning that normally I would be doing this stuff actually on a server. So normally I would SSH into, say, one of the servers like NCC, and I would forward some local ports through, and then this is now on the NCC server, and you can get access to NCC if you email Rob Powell if you want. And NCC has access to quite a lot of powerful GPUs available, but you don't need to do this, and also you would have to do this over say the university VPN if you wanted access to it. You don't need to do this at all, or from within the university network, just because Google Colab actually gives you even better GPUs than some of these that are available for free. So this is completely not required for this course. So you can do this on your home GPU, or you can get access through Rob to access NCC if you want to, but it's really not a requirement. Anyway, I'm just going to do this all on my local machine, where I have access to a single GTX 1080 here. Okay, right. So the first thing I'm going to do is set up Visdim. So I've already pip installed Visdim. So what I'm going to use is something called tmux, which basically opens another terminal which is persistent and always running. So this is very useful because I can just leave this running in the background. So I'm going to go into my activate my mini Conda environment, my Python environment, and I'm just going to type Python -m visdim.server, and I'm just going to say I want Visdim to be running on this port here. Okay, and that's running now, and it says you can go to this web page, and I could forward that port if this was actually running on a server, so I can access it from my home machine. So if I go to that web page now, you'll see I'm in this new web page here, which is the Visdim environment. So within tmux, I can press Control B followed by D to detach the session. Now I'm back to this shell, but actually it's still running in the background, so it's persistent. Okay, so now I'm going to run Ipython, and I'm going to start by just importing Torch, and I'm going to import Visdim. There we go. And I'm just going to basically connect my Visdim to that server which is running. So I'm going to go viz equals initialize Visdim and tell it which port it's running at. Okay, so now it's connected to this, so I could do, for example, viz.text hello world. And you can see it's printed out hello world here. So if I typed hello world again, it's going to create another hello world window. So what's normally best to do is to specify some window string here, so just call it anything we like. And if I just clear this session, Now I can call this as many times as I like, and it's always going to just override that window. Okay, so let's start by just creating some image of noise. So if I just do viz.image and create some random image, so torch.rand, and we could just say I want it to be a free channel image, so red, green, and blue, followed by 256 and 256. So let's do that. There, so we've created this image here, and it's got some random noise in it using Wisdom. And the nice thing about Wisdom is that you can it's dynamic. It updates on the fly. So if I was to create like 200 here, go through a for loop 20 times, sorry, or maybe even 200 times, and if I was to call viz.image with this torch.rand, if I was to forget to specify which window it was, it's gonna open up 200 windows here. So it's important that you remember to specify which window it is you're sending the data to. So I'm just going to run this now, and you can see it's just sending lots and lots of noise to my Wisdom environment. So within Wisdom, you can actually save your sessions as well using this folder up here, and you can maintain all your environments, and that's useful for comparing your results to previous runs if you've been training lots of models and you want to see how you did in the past, see if you're actually improving. So just to show you some examples, I'm just going to clear this, and I'm going to select something from before. I don't know, there's lots of things. I haven't used this machine for a while. So let's just have a look at that one. It takes a while to load because this has got some big files in it. So here's some results I had from some experiments I was doing before with some protein docking. Let's have a look at one more. Let's have a look at this one here. So here I was training on some data set which has some interesting cycles and patterns in it, and you can see you can plot various graphs according to this data set. So Wisdom's a very useful tool. It supports lots of visualizations out of the box. But if you're using Google Colab, you can just use matplotlib, which is equally as powerful. Right, so coming back to I'll just show you some more visualizations. So within Wisdom, you can do like line plots. This is just showing, let's go back to the main environment. There we've got a line plot with some random data in there. You can do histograms. Again, just showing histogram from some noise drawn from a normal distribution. And you can also do like three-dimensional scatter plots and things like that. Okay, so that's really Wisdom. Let's get back into sort of learning about PyTorch and the kind of basic things we do. I'm going to just clean up that. So PyTorch has a very similar API under the hood to NumPy, in which it manipulates these multi-dimensional arrays called tensors. So let's just start really clean again, so we make sure we're starting from the beginning. So we're going to just start by importing Torch, and we're going to start by just initializing a tensor filled with zeros. So if I look at this now, it's got 10 zeros. It's actually a rank 1 tensor, or what we would call a ranked 1 tensor, which is the same as a vector. If we had a rank 0 tensor, this would be the same as a single scalar number. And a rank 2 tensor, which I'll create now, x equals torch.zeros 10 by 10. You could think of this like as a 10 by 10 image or a matrix. This is a rank 2 tensor because it has 2 dimensions or 2 axes. And we could similarly create a rank 3 tensor like this, 10 by 10 by 10. So this has 3 dimensions or 3 axes. Okay, so tensors really are just multi-dimensional arrays, but later we'll see we have some additional functionality added to them as well. So let's just go back to our creating a vector with 10 elements in it. And we can just inspect them here. So PyTorch supports all of the kind of standard broadcasting operations that you would get with, say, a library like NumPy. So if I do x plus 2, it adds 2 to all of the elements because it broadcasts this 2 along each of the elements. And then we could do x plus 3 and times it by an identity matrix with 10 elements. And this is going to broadcast the, in this case, the rank 2 tensor of the identity matrix to the rank 1 tensor, which we've added 3 to, which is going to therefore give us a identity matrix where along the diagonal we have all 3's because we added 3's in here. Okay, so you can squeeze and add, you can unsqueeze and squeeze the dimensions, so you can increase the rank or decrease the rank of the tensor using the unsqueeze and squeeze commands. And so let's just show an example of this. So just x.size. Let's just clear that actually. So there's x. So let's just add another dimension. Sorry. X.unsqueeze. And we're going to add this as the first dimension. So you've probably seen already, but it's just like in NumPy, the elements start from 0. We start counting at 0. It's 0 indexed. So the first dimension is actually called the 0th dimension, and the second dimension is called the first dimension, and so on. So in this case here, I've unsqueezed it along the 0th dimension, which means I've added this new singleton dimension inserted in this position here. Similarly, if I did, and I haven't actually, and similarly if I did, let's just have a look at x. So now if I did x.unsqueeze 0, it would put another one in here. If I did it 1, it would put 1 in here. And if I did it at 2, it would put 1 after the 10. So let's just do that. X equals x.unsqueeze 2. So now you can see I've added a new singleton dimension here. So we now have a rank 3 tensor. Okay, and similarly you can squeeze along these. So I could do x equals x.squeeze 0, 1, 2. So I could get rid of that one. And there we have it. And normally if I just did like x.squeeze, say 0, let's just do dot size. So normally PyTorch won't actually do the operations in place by default. It will just output what they are. It won't actually modify the variables. But you can do in-place operations if you want to avoid a memory copy in some situations where you want to optimize your code. You can use an underscore, and that's going to actually modify x in place. So now if I look at x, it has actually removed that first dimension. So now it's a rank 1 tensor again. You can do all of the kind of standard indexing that you would expect to see with a library like NumPy. You can also repeat along dimensions. Let's just start by looking at what it's like to repeat. So x.size, let's just unsqueeze this a couple of times. So x equals x.unsqueeze 1, unsqueeze 2, unsqueeze 3. So I've added a bunch of singleton dimensions in here. So I could now repeat the data along some of those axes. So I could say like x equals x.repeat 1. So we don't repeat along the first dimension, we repeat the data 3 times along the second dimension, don't repeat it along the third dimension, and we repeat it 4 times along the fourth dimension. There we go, I've just done that. So now we have like quite a big multi-dimensional array with it's a rank 4 tensor. And similarly, you can support all of the standard indexing. So if I wanted to index the 0th element along this first dimension, I could just go like x0, and that's going to give me, it's going to give me the 0th element and all of the data along these dimensions. Similarly, I could get like the first element along that first dimension like that. You can select all of the data in one of the axes or dimensions with the colon operator, just like in NumPy. So in this case, recall our original tensor was this size here. And if I do colon, it's like selecting all of these elements and then just the 0th elements along this dimension. So the result is all of these. Then the 0th one from this third dimension, and then these 2. And you can also, just like in NumPy, you could say like everything up to the first 3 elements of this dimension. So you selected all the first 3 ones there, or you could say like everything from the first 3 elements onwards along the first dimension. And now you've got the remaining 7 elements selected. You can also review, like, let's just go look at our x.size. You can also like view your tensors in different ways. So how many dimensions have we got here? 4, 8, 12. We've got 12 times 10. We've got 120 elements. So we could do like x equals x.view 120. And now you could see we've got a vector of 120 elements, or you could do like x equals x.view, put in anything you like really, so long as it adds up to 120. So we could do like 10 by 12. Okay, there you have it. So tensors by default are stored as floating point 32-bit floating point numbers, but you can change your type however you like. So you could do like x equals x times 10 and make that into, sorry, didn't mean to capitalize that. Change that to long types, so d type. So now they're 64-bit integers. And you'll see we've no longer got the decimal points in here. And then you can cast that back to floats just by like doing x.float. And the really cool thing about PyTorch, which is really exciting, is that you can actually change the device of tensors very, very easily, which means we can send them onto the GPU. So by default, you'll see that your tensors are actually on the CPU, but you can just do x equals x.CUDA whenever you like. And that is the first time you do it, it takes a bit of time because it has to sort of boot up your driver. But after that, it's really, really fast to just move data from the CPU to the GPU. So now if we look at the device, this tensor is now on the GPU, which means every operation you do on it results in a GPU tensor, and all of the operations are subsequently performed on the GPU. So that's really, really cool. If you want to make your code run a lot faster, you can just, at the beginning, switch your tensors over to GPU tensors and so on. Okay, so that's a very brief run through of PyTorch tensors. They're effectively just multi-dimensional arrays where the number of dimensions we have corresponds to what we call the rank of the tensor, where rank 0 tensors are scalars, rank 1 tensors are vectors, and rank 2 tensors and onwards are matrices, and then higher order multi-dimensional arrays as we get into higher and higher ranks. But yeah, you can have like rank 10 tensors, but remember that you'll start to run out of memory quite quickly if you start initializing huge volumes. Okay, so let's now look at how Torch handles data loading and data parsing. So I'm just going to import a bunch of libraries here, NumPy, Torch, a neural network, part of Torch, and a functional interface of Torch, which just has like a load of logical functions in there, and also Torch Vision, which has some specific image processing like functionality added to it. So I'm going to import Wisdom this time, and we're going to just say, again, Wisdom is on this port here. And I'm going to start by just defining a set of transforms, which means that every time we read an image from the hard drive, we're going to apply a set of operations which basically resize it and normalize it to make it into a fixed size, which is better for training. There are some neural networks which can operate on dynamic or different sized images, like fully convolutional neural networks, for example, or recurrent neural networks. But it's a lot easier for the simple neural networks to just have all of your input images or input data as the same fixed size tensors. So here's a sort of standard stack of transforms. We're going to take an image from our hard drive, and we're going to randomly resize it and crop it to 224 squared. So it's just going to like randomly select a 224 squared image or region within a large image, and crop it at that region. If the image is too small, it's going to sort of resize it to be 224 squared. then it's going to randomly flip it horizontally, which is fine if you've got like images of natural scenes like trees and things. Then we're going to turn it to tensor. That's going to actually change it from like a Python image library object and change it into a PyTorch tensor object. Then we're going to normalize it, and this normalization scheme is like what standard for like ImageNet, or it's just like normalize it to sensible ranges as we like to deal with them. And we're going to define, so this is the transforms we're going to apply for data when we do training, but when we do testing, we generally don't want to like randomly crop the images. We want to just like take a fixed central crop or a fixed resize. So we tend to have a different set of transforms to our testing conditions. So here's the testing set of transforms. We're going to just resize all the images to 256 squared. Then we're going to just crop out the center part from them so there's no random part in there. And then the rest are the same. And in this case here, I've downloaded some data already. So I've downloaded some ants and bees data sets. So if we just have a look at some of the data, I've got these two folders, this training folder and this validation folder. And this is going to be the data we train on, and this is going to be the data we test on. And generally we don't want these to be, well, they mustn't be the same data, but even we would like them to actually represent different distributions of data. So maybe these were all photographed down in Devon, and maybe these are some from ants and bees photographed in Durham using a different camera and so on. So within the training data set, we have two classes. You could have lots of classes here. We could have ants, bees, horses, and kittens. And then with in the ants folder, you can see we've got various images of ants from different sizes, different scales. And similarly within the bees, we've got different images of bees. Okay. So I'm just going to use the PyTorch built-in functionality from Torch Vision to specify this is an image folder dataset, and I'm going to just say which transform stack I want to apply when reading these images. And that's done. And we can have a look at the class names. We can see it's already recognized the two folders as being called ants and bees. And it's quite easy to set up your own data loaders. If you've got like a spreadsheet of data, it's quite easy to set up like a tensor data set which has the functionality to read the data from the rows and columns accordingly. So once you've set up your data set, we have what's called a data loader, and this is basically responsible for taking our data set and splitting it into smaller batches of data which we train on. Normally some of these data sets can have thousands, if not millions, of images or millions of audio signals or text, whatever data, and you could never fit it into memory. And the algorithm we used is called stochastic mini-batched gradient descent. So what we do is we tend to randomly sample a small batch of data from our data set, and then we just train on that small batch of data. Then we randomly sample another small batch of data from our large data set, and we train on that. So this part here is responsible for grabbing a random small batch of data, and it's also responsible for shuffling it, and it's responsible for maybe distributing that data onto different processing threads. So we basically create this torch.utils.data.dataloader object, and we specify what our data set is, and we give it some parameters like how big we want our batch size to be. And in this case, I only want to train on 4 images at once, and whether we want to shuffle. So when you're training your data set, you always want to pick out different batches of data when you're training, but when you're testing, you just want to test everything in the same order, so you don't need to shuffle. And the number of workers or number of processing threads we want to use, and that depends on what computer you've got, whether it's a large server, whether you've got lots of I/O to do, in which case you want more threads. Okay, so let's define the loader and test loader, and then you can iterate through your training loader object. So it's got an iterator in it, so just do X label and pull out the next element from that iterator. We can see now we have a batch of 4 images, and each of them, they're color images, RGB channels, and they're 224 squared, so they're quite reasonably large. Now I'm going to just visualize these images, and this is just a bit of code I wrote to normalize them and put them in a grid, and we can then just send that on to Visdom. So if I just go on to Visdom now, close those old things, you can see now we've got a batch of our data sampled. Let's have another look at another batch. So we can just call this function again, and then that's going to pull out another random batch according to our data loader. And again, we'll see we've now got a batch of 4 images sampled, which we're going to train on. Okay, so I'm going to show one more example now. That's for ants and bees. We can also just use one of the built-ins. This is Fashion MNIST, which is quite a popular data set where you've got these very small 28 squared images which contain fashion items. I'm resizing them to squared just because it's easy to train with the power of 2. So let's just do this. So let's create our define our data set and wrap it in a data loader. A much larger batch size this time. We can have 64 elements in each batch because they're smaller images. And again, we're going to just pull out a random bit of data. So if we do x.size, now you can see we've got 64 images in our batch. And these are just grayscale images. They don't have any color information, so we just have one channel, and they're all 32 squared. So also I've also got access to labels. So these are the actual classes. If I just look at the label, we've got just a vector of 64 elements where each number tells us which class it's in. So maybe 1 is all the ones are like handbags, and all the 8s are shoes, or so on. Again, let's just visualize some of the data. There we go. You can see some of the data there. A random batch of sort of shirts and ankle boot shoes and handbags and so on. So there's examples if you're interested in doing applications with natural language processing in text. You can go on PyTorch.org and look at some of the text tutorials. There's also tutorials for other domains, such as working with audio, Torch audio, and so on. Okay, let's start again, nice and clean. I'm going to look at actually doing some training to backpropagation algorithm. So again, we're going to just import Torch, and we're going to create a rank 2 tensor. So x equals torch.zeros. We're going to just say there's 16 by 16 elements in it. So let's just see that. There we go. It's a matrix with 16 rows and 16 columns. And if we look at the requires grad variable, so every Torch tensor by default has this requires grad, and it's false by default. Okay, so if I just created another tensor now, so z equals x plus 2, so I've got z now, and you can see it's just all 2s. That's a bit easier to see, isn't it? If I just look at z dot grad function, there's nothing there. And if I look at z dot grad, again, there's nothing there. Okay, so how does automatic differentiation work in PyTorch? What do we actually do? Well, if we let's just delete x and start again, nice and fresh. So start by creating x equals torch.zeros, 16 by 16. So we're just recreating it now. But this time I go x.requires grad equals true. Now basically PyTorch starts to keep track of everything I do to x under the hood. So it starts to create a computational graph just as I start doing operations on x. So this is what's called a dynamic graph, and it's really incredible what happens. So if I just start to do z equals x plus 2 now, and now if I look at z.grad function, you can see it's got some information here. This is effectively starting to create a graph under the hood. It's keeping track of everything that happened to x and all of the subsequent operations. So z also, if we look at requires grad, you'll see it's true as well. So I could now do like z equals z times 3, and I can look at z's grad function now, and you can see it's now multiplied backwards. So it's kept track of this operation, which itself has kept track of this operation. So it's creating this graph implicitly under the hood, just as I do normal Python code. I don't need to create these graph objects manually, and so on. So I can actually go back through the graph anytime I like, just by doing like z.grad function, and then I could access like its parent. What have I done wrong? Sorry, grad function dot next function 0. Sorry, there we go. So I've gone from the z grad function, which was the multiply backwards, and then I've sort of accessed its parent, which is the add backwards function. So let's say you've built some neural network this way, which creates this large complex graph going through all of these operations. At the end of the day, we want to have some loss function, or remember from our previous lecture we said we want to reduce all of our operations to a single measure, which tells us, or metric, but the performance measure tells us how good or bad the neural network is. So we reduce it to a single number, which we try to minimize at the end of the day. So let's just say our loss, let's call it a loss, equals in this case z.mean. Okay, so loss also has a grad function, the mean backwards one. And if we look at this point in time at our gradients for say x, there's nothing there. We haven't yet computed the gradients, or we haven't yet computed the gradient of the loss with respect to x, I should say. But here's the really clever part. If I now do loss.backwards, this under the hood does the backpropagation algorithm, which basically goes backwards through that computational graph, using any intermediate variables which were already computed as I constructed the graph in the first place, doing what's called the forward pass, and it differentiates computing the gradient of the loss with respect to any leaf variables in there. And remember, our very first x was a leaf variable which requires grad equals true. So we'll get the partial derivatives, or the Jacobian, where we'll have the gradient of that loss with respect to all of those leaf variables. So now, if I do x.grad, we have all of the gradients in there. So we know now whether to increase or decrease all of those values for x a little bit, such that we can minimize that overall loss. So if I wanted to, I could do x equals x minus, say, some small amount, 0.1 times x.grad, and this will actually update x a little bit in the negative direction of the gradient, such as to minimize the overall loss. And that's really an amazing thing that's happened under the hood to make all that possible. I remember it going back several years ago to doing differentiation. I would write thousands of lines of CUDA to do this kind of similar stuff, and the fact that we can do it in just a couple of lines of Python code and have it all super optimized on the GPU is just remarkable. It's very difficult to, especially when you build up large problems like level set methods or so on, where you've got lots of terms and operators, just to be able to get this all for free so easily is a huge advantage. And actually a lot of deep learning is just driven from this kind of advanced tooling that we see. Okay, so that's a kind of very brief view of backpropagation and how it works. Let's now sort of layer up and build into some more advanced architectures. Well, we'll start by just building a manual classifier. So we're going to train a deep neural network to classify some images. So we're going to start by just having the same kind of imports again. We're going to connect up Wisdom. Okay, oh, I forgot to clear all of the previous data, so let's just start by creating two empty graphs, which we're going to use to store our classification loss and our classification accuracy. We're going to just say this should be running on the GPU. This is just a helper function I like to use, which makes it easier to pull out data from a dataset without having to iterate through the whole thing. This kind of idea of cycling through. And we're going to again use the fashion MNIST dataset, where we're going to have a train loader and a test loader. So the training loader just contains like all of the training data, and the testing data is some different data which isn't in the training dataset. And we're going to just see how big these datasets are. So there's 60,000 images in the training dataset, and there's 10,000 images in the testing dataset. So now we're going to define a very simple neural network, and this extends nn.module. So everything that extends nn.module, all these classes, you have two main functions in them. You have your init function, which initializes the neural network. And this is basically where you initialize all your parameters and you say what their initial values should be. So if you've got like a deep neural network with convolutions, or a deep neural network with lots of linear layers, this is just going to be like where you store all of those parameters and in what form they're stored. So in this case, we're going to store all of the parameters of two linear layers, so two fully connected layers, which have, and the first layer has 1024 input features. Why 1024? Well, our images are 32 by 32, and 32 by 32 is 1024. So this first neural set of neurons, it's actually got 512 neurons, and every neuron has 1,000 edges connecting to every single pixel in the input image. And then we've got 512 of those neurons. That's quite a lot of parameters already. That's 512 by 1024 edges in that first layer. And then the second layer has 10 neurons, and each of those connect to all of the 512 neurons from the previous layer. So that's got 5,120 edges effectively in that layer. So it outputs 10 neurons, which we're going to use to estimate the probability of which class of image is being detected. So whether it's a shoe or a handbag, that's what each of those 10 neurons is going to say. So we want those 10 neurons to output a high probability, so like a 1, whose index is of the class we're after. So it's a probability distribution over the classes. That's what we want to learn. And then it's got this forward function, and this is where you actually do the operations, you do the logic. So in the forward pass, it's where you actually like do your multilinear map, your weight matrix multiplied by the inputs, and then you add the bias or so on. And then this is where you would actually do your nonlinearity function. So this is where you would then take, if you're using values, where you have the max of 0 and x, it's where you would actually do that part. So let's define that class. And then we're going to just say our network and initialize it. And we're going to then shove it onto the GPU, .toDevice. So the first time it does this, again, it has to warm up the drivers a bit. And I've already specified the device should be CUDA, so that's just saying to CUDA. And then we're going to initialize our epochs. Epochs are basically, one epoch is an iteration through the entire training set. I guess in this case I'm not really doing entire epochs, I'm going sort of for 100 elements at a time, but it's fairly similar. And then we're going to start our training loop, and our training loop is normally just like while true or up until some terminating criteria. In this case it's just doing 100 epochs. It's just going to initialize some arrays to collect up some of the measures, and then going to iterate through some of the training data set. In this case it's going to do 100 batches at a time, and it's going to just grab some data from the batches. So x.size, each time we call this, it's going to grab a new batch of 64 images. It's also going to give us t, the classes that they're labeled as. These are annotated images. This is supervised learning we're doing. And then what we're going to do, so let's just do this manually from now on. I'm just going to initialize this. I might use it. So first of all, we're going to pull out a new batch of data, and then we're going to go for each parameter in the neural network. Okay, if the and we're just going to basically initialize the gradients, or initialize the gradients as 0. So make sure we're starting nice and clean. So all of the grads are now zeroed out. And just in case there was some gradients left over from the previous iteration, we're just going to make sure all of the parameters, all of the leaf nodes, all of their gradients are all zeros at the start. It's nice and clean. Now we're going to take our x, and we're going to just view it as a, remember the first linear layer was 1024 input, so we're going to just view that as a 64 by 1024 tensor. So we're going to do x.view, x.size 0, so 64, I could just write 64 if it's clearer, 64 by 1024. Okay, looks like that. Or you could just do this like notation here, which is the same thing. So x equals x.view, and this is x.size 0, which is 64, and then -1 is just like saying squeeze all of the other dimensions down. So 64 by 1024. And then we're going to feed that data, this is our raw image data, into our neural network, and we're going to get some predictions. So p equals nx. And this is the distribution we're trying to learn over the output of our network. So p is just a bunch of numbers right now, and if the size of it is 64 by 10. So this is the probability we're going to be trying to learn over the classes. So the actual prediction is the argmax, or the if we just look at one of these, so like p0, one of these, the data for one of these images, from all of these probabilities, the maximum one, maybe it's this one, maybe it's actually this one. This looks pretty big, 1, 7. Probably this one here, I might have made a mistake, but this one looks like the maximum. So this 0, 1, 2, 3, 4, 5. So this is basically saying like it thinks it's the 5th class. It's the highest one. So let's just see that. Pred equals p argmax. So if I just do like pred 0, indeed it's the 5th one it's saying. And then the loss we're going to minimize is the cross entropy, which we'll come on to what that means, but it's basically a loss which works well for categorical classification. We'll discuss that in a later lecture. But this basically just gives us a single value which tells us how close the prediction is to the ground truth probability distribution. So we tried to make the prediction distribution identical to the ground truth probability distribution, which just has a 0 at the 5th index, or whatever the answer is. Okay, and then we backpropagate this loss, and now all of our parameters in our neural network will now have the gradient of that loss with respect to those parameters computed. So we can now just move every parameter for p in the neural network parameters, move every parameter a little bit in the negative direction of the gradient. So that's gradient descent. And that means we've moved or tweaked all of our neural network parameters up or down a little bit, such as to minimize that overall loss. And then we can just sort of append some statistics. And then we go through our training loader, our testing data set, and we just do the same thing. So we can see like how accurate our model is. And then we plot the metrics. So let's just run this now in a loop. And have a look at the code on Wisdom. So you can see it's training now, and this is the test accuracy. It's already about 70% accurate at the beginning. Well, it started off at 40% accurate, and now it's already 77%, 78%. And the training loss is going down, the error is going down, and the accuracy is increasing. Let's see if we can get to 80% accurate. There we go, 81% accuracy. And you're already just starting to see a little bit of divergence where the training accuracy is slightly better than the testing accuracy. And this indicates that there's some overfitting already starting to occur in this neural network, even though it's just a very simple neural network. It just means that the training conditions don't quite match the testing conditions. And here you see the similar thing. You see the training loss is a little bit lower than the testing loss. Okay, so that's training a deep neural network. So normally in PyTorch we don't manually do the gradient descent ourselves. We would use an optimization algorithm. So here's another example just doing this. All of the first bits of the code are the same, the network's the same, everything's the same up until this line here. So I'm just going to reload all of that. But now we use what's called an optimization algorithm, which basically does the gradient descent process for us, but it does something a little bit more sophisticated. So we define this optimizer, and most of the time you just use Adam. Adam is a very, very famous algorithm. It's not always the best one to use, but 90% of the time or 99% of the time, it generally just works very well out of the box. There's various articles about what you should use and why, but most people just use Adam. So we use Adam to optimize our neural network parameters. So we pass Adam the name of, where all our parameters are. We give it some initial learning rate, which is very important to get this right. Normally it's about 1e to the minus 3, or 3 to the minus 4 is a famous number people use. But again, you just need to play around with and see what works well. Then everything's the same, except that now, after we've done loss.backwards, so this is all the same as what you've seen before, but after you do loss.backwards, instead of manually, like, for each parameter moving them all in a little bit in the negative direction of the gradient, now we just do optimizer.step. And under the hood, this does the same thing, but it does something a little bit more sophisticated based on the Adam algorithm, which is basically like it keeps track of individual learning rates for every parameter, so it can make move some parameters more quickly and move others slowly, and it has like some momentum in there, so it's like they speed up and then they go very fast and they slow down again. It's actually like a second order model, but it's a bit sophisticated, but it works very well in practice. So this is the same thing again, so we could just run this, and we should see right at the start, you can see it's now already at 82%. So you see how faster it was to use Adam. 84% now. A little bit more bumpy, but you can see it's already a lot at 85%, 86%. So you can really see how effective Adam is compared to stochastic gradient, just standard vanilla stochastic gradient descent. Okay. All right, and one last example. Let's see how we are for time. Okay, doing all right. So here's another example, but this time I'm going to introduce convolutions. So this is a convolutional neural network, and before I get onto that, I'll just explain briefly what convolutions are manually. So let's start by just clearing up our session. I'm just going to import Wisdom and PyTorch, connect them up, and I'm going to use this helper function to normalize the data. This is just so we can visualize some images later without overflowing. I'm going to just set up a fashion MNIST data loader again, and I've just pulled out some of the data here. So if I do x.size, we can see we now have like a random batch of 64 images, which are all one channel grayscale, and they're 32 squared images, so they're very small images. I'll just clear up that graph from Wisdom. And I'm going to just define a convolution now. So, so I think, what was this one doing? 311. Okay, so I'm going to create a convolution function. So it's an nn.conv2d, and I'm going to say, because it's a grayscale image, it's going to have one input channel and one output channel. So it's just like a single convolution, like a Gaussian blur or an edge detector. And and the most famous pattern we'll describe these a little bit later in a future lecture, but it's the 311, a convolution with 3 by 3 weights. So a kernel size, if I can spell it right, kernel size equals 3. And if you remember, we add some bias vector, but most of the time that's not very important, so I'm just going to say bias equals false for now. So this defines like a convolution constructor, and we can look at the weights of this convolution, conv.weight, and in this case you can see they're already initialized randomly, which is very useful because we want to start all in different places in the optimization landscape. So the size of it is 1 by 1 by 3 by 3. These ones here correspond to our number of input channels and output channels. So I'm just going to, if I just like actually apply this convolution on the data, we can actually just see it. So I can just basically do conv on x, and this actually applies the convolution to x. So this gives us, in this case here, it doesn't have any padding. Maybe I should add a bit of padding, but But we can just have a look at x basically. So this is the result of just the first random convolution which it gave us. And we can manually set the weights to say some edge detector. So I've done it here. This is just a bit like a subwall detector. And if we just look at the output now, you can see we've basically got this edge detector now by manually setting the weights. So I'll come on to this a little bit more in the future, but basically when we do convolutions with convolutional neural networks, we wouldn't just do one convolution at a time. We would actually do, say, we don't want to just learn one set of edges, we want to learn lots of different ones. So we would do, say, 64 convolutions. So maybe we'd have like 64 here. And if we now were to look at the weights, we now have to learn 64 different 3x3 kernels. And that's only if you've got one input channels. Actually, with deep neural networks, if you've got lots of input channels, like an RGB image, you would actually do a different convolution for each input channel separately and stack those up. So if we had like 3 input channels, we would actually now have, or maybe make it clearer, if we had like 4 input channels like RGB and alpha, we would now have 64 separate convolutions, so like Gaussian blurs, edge detectors, blob detectors, texture detectors, color detectors, for each of the channels done separately. So we'd have quite a lot of parameters, 64 by 4 by 3 by 3 parameters to learn in that first layer. So that's kind of briefly how convolutions can be constructed and done manually. Now let's build a convolutional classifier. So again, this is all the same as we've seen before. This time I'm going to do a much harder classification problem, which is Sci-Fi 100. It's a very difficult data set to classify. It's got 100 different classes: bears, beavers, beds, beetles, bicycles, bowls, bridges, butterflies, camels, castles, caterpillars, and so on. So a lot of classes and not a lot of data to train on either. So I'm just going to initialize that. So again, you've only got 50,000 images to train on, and you've got 100 classes to classify between. So it's quite a hard problem, this. So we're going to use a convolutional neural network, where we're going to basically we're going to use 4 by 2 by 1 convolution. So our kernels have again, we'll discuss this in the model in I think lecture 4 or 5. How a lot more about these properties, but basically it's 4 by 4 kernels, and they have this stride parameter, which means it skips over every other pixel effectively in your image. And we're just going to basically say it starts as a color image and it outputs 64 features. Then it goes from 64 and it does a convolution followed by some normalization followed by a rectified linear unit, our nonlinear activation function. Then it does and then it goes from 64 features to 128 features. Then it goes from 128 features to our final 100, which is actually the number of classes we are trying to classify here. Okay, so we'll just define our convolutional neural network like this. We'll put it on the GPU. And we'll just see how many parameters are in this neural network. So it's got 339,000 parameters, which is sort of fairly small actually in terms of neural network standards. Especially given how complex this problem is we're asking it to solve. Okay, and then the rest is all the same. We're going to learn a distribution over our classes and try to make that distribution max to the ground truth distribution, which is the ground truth annotations of what each class should be. And we're going to just train this. And as you can see, it's already training, and it's about what is that, 10% accurate already, and that's going to keep increasing slowly over time. So okay, so as with this lecture here, there's collab versions of these materials that you can play with. So in the first version here we have if you go onto Duo, you can see a Google Colab link for the classifier, where we just basically classify some data from fashion MNIST using just simple linear layers. So you can have a look at that, and you can see how the test accuracy increases and the training loss decreases. And then we can see the predictions here, where you can see here it's got it wrong. It thinks this is a sneaker, but actually this is a sandal. And you can see the distribution it's learnt, so it's not quite sure whether it should be a sneaker or a sandal. And similar here, it thinks this is a pullover, but actually it's a coat. So it's kind of making that sense. It's the things it's getting wrong are a bit non-trivial. And also there's the code here for a convolutional classifier on the Colab 2 link. And this is the sci-fi example here, where you've got hundreds of classes, and this is the same architecture you've seen. It's not a very good architecture, especially at the end here. It should probably have some more layers, I would say, so you don't need this average pool at the end. But it's just an example architecture, and it gets to about 26% accuracy after a small amount of training. I'm sure it would get a lot higher if you trained it for longer. And so you can see there's 100 classes, and this is the distribution it's learning over those classes, and it gets it right some of the time. Skyscrapers, rockets for some easy ones, and it gets it wrong, so it thinks this whale is a computer keyboard. So yeah, have a look at that code, have a play with PyTorch, have a look through some of the tutorials in your own time. I hope this sort of makes things a bit clearer to you, and that you feel a little bit more confident now to go ahead and just start learning, running through some of the tutorials and studying in your own time. Maybe you could look at some of the interesting architectures from other people's code on GitHub and explore around and see how they've been writing code, see how they're building neural networks in terms of blocks. So they define these blocks of functionality and add the blocks into their networks, so that they don't need to keep writing out lots and lots of code in their neural network as they get more complex. Alright, well that concludes this lecture. That's it. I hope you have a good week.